In pricing this option over a 2-year period, let's make a couple of points. First of all, the option was priced by working backwards through the tree. This is sometimes called a backwards substitution. The option for 2 years was greater than the value of the option for the 1 year. A couple of other points. The delta and the B representing our T-bill position, changed at each node. And this is an essential idea in the replication of options. And that is that as you move through time, you must constantly rebalance between the stock position and the T-bill position as you approach maturity. And we saw this in the earlier diagram about delta. And that is that if you're replicating an option that's moving into the money, delta is going to approach 1, which means you need more and more stock as you move through time, ultimately to have the stock in hand at exercise when the long position in the option exercises and buys that stock. On the other hand, if you're replicating an option that's moving out of the money, its delta is approaching 0, and that means that as you move through time, you'll be selling some of your initial stock, repaying your initial T-bill position, and as you approach maturity, there'll be no exercise, and your replicating portfolio will have a value of 0. So what I'd like to do now is to show how in the instance of a European option, we can actually calculate the value of the option at time 0 directly from the option values at time 2 years. And that we'll see this generalized further in the subsequent module, and we can use backward substitution as was just illustrated, but this is a more direct approach that works for European options. And let's in fact do the algebra. Let's implement the algebra of the earlier example. So first of all, we have that the option value in the up state is a present value, and I'm going to use P rather than P star, but my P is the P star of the book, just to make it a little easier to write. So I'm going to use P star CUU plus 1 minus P CUD. So that was the formula. That's the expected present value of the option in the up state. We similarly have the value of the option in the down state. Now we're applying P to CUD, and we're applying 1 minus P to CDD. Finally, the value of the option at time 0 is the present value of these two option values that we just calculated, P times CU plus 1 minus P CD. Now if we insert both of these expressions in here and do the algebra, we will get e to the minus 2 RH. We're going to have a P squared CUU 2 P1 minus P CUD and a 1 minus P squared CDD. Notice that this would appear to be a straightforward generalization of Formula 10.3. In Formula 10.3, we have a present value of expiry values of the option, and we put weights on those expiry values according to the risk-neutral probability P. Notice how this does the same thing. It does a present value for 2 periods, and it takes the year 2 option exercise values and applies an expected value using a 2-period binomial. If P is the probability of an upstate, this is the probability of two upstates. This is the probability of an up and a down, and this is the probability of two down. So this is a straightforward generalization of the notion of what's called an expected present value. The expected uses the binomial probabilities of the states at expiry, up, 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 down, and down, down. And the present value is at the risk-free rate, 2 periods instead of 1. This formula will be generalized further in the next module, where we'll look at multi-period option pricing.